The magneto-optical trap was an invention, really a quantum invention, that enabled lots of people to start using cold atoms to do experiments. Now, the first thing that I have to say is, what do I mean by cold? And what is the good of cold atoms? What I mean by cold is, first of all, measured on the absolute zero temperature scale, the Kelvin scale. So the temperature in the room here is 300. If it got up to 320, that would be hot. If it got to 250, that would be really cold. And we're talking about going to 1. Well, not 1, going to 1,000th. Well, not even 1,000th, going below 1,000th. And what's the difference? Well, the difference is that if you're at room temperature, atoms move as fast as jet airplanes. And if you're at 1 millikelvin, 1,000th of a Kelvin, then atoms move as fast as an Olympic sprinter. That is to say, that's pretty slow for atoms. Now, why do you want atoms to move slowly? Well, 2 reasons. One, if you're making measurements on them, then as they speed along through your apparatus, they're in it for longer. And so you have more time to make measurements. Secondly, if you want to study the weak interactions between atoms, you want them to be very cold, because the temperature is a measure of how fast they're jiggling. And the faster they jiggle, the harder it is to see the interactions that they have, because they just escape from each other's forces. So what is the magneto-optic trap in particular, and how did it come about? There are basically 2 ways to trap. This is even better than watching a cold atom go through your apparatus, would be to be able somehow to hold it. But of course, you couldn't hold it in any object, any physical object, because that object would be at room temperature, or it wouldn't be as cold as the atom. So therefore, you have to use something like laser light or magnetic fields, or something that is not really material. For a long time, it was known that the greatest force that light could put on atoms was just to bounce the photons in the laser beam off the atoms, and that would push the atoms so that they get a good speed, maybe as fast as a rifle bullet, only when you push them this far. So the laser could have a tremendous, what's called spontaneous force. However, it was proved that you couldn't trap an atom with the spontaneous force. And so people were not exploring that particular avenue towards getting trapped atoms. And we once had a speaker here named Alan Aspect, who's quite a famous physicist, who mentioned a thing called the optical Earnshaw theorem, which basically explains why you can't trap atoms by using this photon pressure from the lasers. And after the talk, one of my students said, "Dave, I didn't understand that comment at all. Please explain it to me." So I started explaining it to him very carefully. And at one point in the explanation, I suddenly realized, oh, wait a minute. That explanation applies to little glass beads. It doesn't apply to atoms, because atoms have spin, and they might interact, depending on which way the spin of the atom is, it might interact more or less with the light. So if I can figure out a way to make the atom go over here and interact less with the light, and then, wait a minute, I want to make it interact more with the light when it comes over here, and less when it goes over there, then if I have 2 opposing laser beams, it'll be stuck in between. And so what the student, Eric Rabb, and I finally figured out was we had a way to make 6 laser beams go and push in such a way that the atom was trapped in the middle. This is one of the magneto-optic traps that we made. It has an X and a Y and a Z axis. And along each axis, the X-axis, there's a laser coming in here and one there, laser beam here and there, laser beam there and there. Now, what it is that makes the atom move, when it moves over to here, interact more strongly with this laser beam than the one of equal intensity going the other way, is that we use a magnetic field in a special way to tune the strength of these forces. That's why we called it the magneto-optic trap, is that the magnetic field causes a change in the interaction between the light and the atom such that for a certain magnetic field, the atom is stuck in the middle. And it's absolutely amazing when you see this thing go. You look in and you shine the laser beam in, and there's a gentle yellow scattered light, the same color as the sodium streetlights, that comes glowing in the whole region. And then when you get it tuned up, suddenly right in the middle there's a bright ball of atoms. And then if you turn the lasers off, the atoms, of course, will start to fly out towards the edge because there's no more trap. But they're going so slowly that you can turn the light off for several tenths of a second sometimes even. And that's the immediate proof that the atoms were going very slowly, that they were very cold to begin with. So now where has this taken the field? Well, first of all, it made it easy for lots of people to start experimenting with cold atoms. As a result of its making it easy for people to do cold atom experiments, lots of people flooded into this field and started doing really innovative experiments. And soon, a millikelvin, a thousandth of a Kelvin, above absolute zero, began to look hot because people figured out other ways to cool atoms off by evaporation or by Sisyphus cooling or by other forms of molasses. And so ultimately the atoms started to get going really, really slowly. And then this led to new states of matter, such as Bose-Einstein condensation. When you have cold atoms, the first thing you think of to do is to do spectroscopy, just to measure some spectral lines much more carefully, or to make an atomic clock, because the atoms are cold, and either you can leave them in the trap, or put them in a different kind of trap. We put them in a magnetic trap. And then you can do experiments on the trapped atoms. Another thing that you can do is look at atom-atom collisions. When atoms collide at room temperature, many quantum states are involved. But when they start to get very, very cold, then there's only one interaction or one number that characterizes the interaction between the atoms. And that's an interesting regime to be in. And it turns out that by changing the magnetic field again, you use the magnetic field to tune little things. You can change the magnetic field and make the interaction stronger or weaker. And that's called the Feshbach resonance. And so this gives you a way to control the strength of how the atoms interact with each other. Well, that suggests that now maybe I can start studying collective effects of atoms. And that has proven to be, I think, the scientifically most valuable outcome of cold atoms, even though it wasn't initially realized that this would be the ultimate direction of the field. So the main areas of research there were, first of all, to make a Bose-Einstein condensate. This was a state of ultra-cold matter that had been predicted years ago, about in the 30s, by Bose and Einstein. They predicted that when you cooled off a collection of atoms enough, that all of a sudden a large fraction of those atoms would all get together in the very ground state of the system. So all these atoms here, a large fraction of the total number of atoms, are in just one quantum state. And they act like a quantum fluid in this case. And you can start studying quantum solid state theories or condensed matter theories using atoms. And the whole thing is so crazy. The temperature is so low that the atoms are farther apart than they are in this room, in the gas in this room. But nevertheless, you're studying phenomena that are characteristic of solid objects. And you can make, of course, as you may know, many solid objects are basically crystalline, because the atoms arrange all in a nice little array, and then the electrons can zoom around in that array. Well, what we can do is to make light, to put the light back in again in what's called a standing wave of light. So the light has maxima, minima, maxima, minima, maxima, minima, and then the atoms are so cold that they will only settle in the minima. And so we can make a solid out of laser light and then you can simulate what the electrons do in a normal crystal by using atoms in place of the electrons. So it's kind of a crazy world, but it's a wonderful world because we can change the strength of the lattice that holds the atoms, or holds the thing together, just by changing the knob on the laser. Make the laser brighter, this is deeper, or turn the laser down, and then the atoms start to move around. And so people have studied a famous transition that occurs between the atoms moving around like a superconductor, or the atoms all staying still. The other area that's really hot now, so to speak, in this ultra-cold atom business is to put atoms that are not bosons, which like to be together, but fermions, which don't like to be together. And that's exactly the same statistics or the same property that electrons have. They don't like to be together. And so now we can mimic a lot of electron systems by using cold atoms to do that. But what is present in a very, very large fraction of all these experiments is this magneto-optic trap that my student and I invented, really in a discussion between the advisor and the student about why some paper that seemingly blocked the route to this, to using light forces to trap atoms, we discovered the flaw in it. And from there, once we saw the flaw, then we were able to ultimately make the magneto-optic trap. As I look ahead now and ask what are the great scientific problems that we might solve with cold atoms, I would say probably the most outstanding one is, what about high temperature superconductivity? About 20 years ago it was discovered that superconductors could be superconducting all the way up to half of room temperature or so. And since then this was obviously a new kind of superconductivity. A new theory was needed for this, and we still don't have that theory. And what we hope is that by making these lattices, or maybe not lattices, or maybe triangular lattices instead of square lattices, that we can understand the theory for these high temperature superconducting materials. And if we could understand the theory and then come up with a real solid state material that had a transition to superconducting above room temperature, then all the wires that you see on the poles carrying electricity around could be made as thin as you want. We could distribute power, we could make very powerful electric motors in a very small space. The technology of using electricity would be tremendously different, and that's the holy grail, is to get there.